1, 5, 17. We look at a distribution to see how a trait is distributed in a population. But you probably already knew that. You probably could have filled that in without a slide. That variation exists in a population. And remember what a population is, because when I looked at your vocab from the last unit, a lot of you for your final part C didn't have this right. A population is what? All individuals of a species in an area that can interbreed. And the distribution just shows that there is some variation in a trait. We could do a distribution table for number of wisdom teeth. Do you think it's possible that there's somebody out there who has 5 wisdom teeth, or 6? I went to high school with a girl who she had a full second set of adult teeth that came down through the roof of her mouth. She had them all removed. I'm sure it was quite painful. She definitely had extra wisdom teeth. She had extras of everything. But you think we're going to find many people who have 6 wisdom teeth? No, it's possible. But there's certainly variation in that there are people who have 0. There are people who have... There's probably somebody out there who has 1, since I know I have an odd number. There's probably somebody else out there who has an odd number. There are definitely people with 2. There are probably a couple more people than just me who have 3 wisdom teeth, who have freaky lopsided teeth. So a distribution shows the percentage of individuals that have a specific value for a trait. In your research, you found that 35% of humans do not have wisdom teeth. 35% of people have 0 wisdom teeth. That's pretty high. It'd be interesting to know what percentage actually still have 4 wisdom teeth. It'll be interesting to see how many wisdom teeth my daughter comes up with, since I have 3. Yeah, of course. There was a time in human history when the percentage of the population that didn't have wisdom teeth was 0, presumably. No, probably not. There might have been 1 or 2 people who were born without wisdom, or who were born without wisdom teeth that we're going to grow up in. If we didn't have that initial variation, we wouldn't have come to the point where we have 35% of the population without wisdom teeth. When a distribution changes, what do we call that? This is not a fill-in. What do we call it when a distribution of a trait changes in a population? That's evolution. Evolution is just the shifting of trait or gene frequencies in a population. That's what we're talking about here. So a lot of you were coming at it from a, evolution is how organisms change over generations. That's true. But in terms of talking about the nuts and bolts of it, it's really how the distribution of a trait shifts over, again, many, many generations. Got here. This is brand new. We have not talked about this before. Equilibrium is when things are not changing, when they are remaining the same overall. And when you did your pre-work on your vocabulary, I'm sure more than one of you looked at that word equilibrium and thought, that sounds kind of like equals. Anybody think that? And I know what equals means because I've been doing math since 1st grade. So equal means the same as. 1 plus 1 is the same as saying 2. 1 plus 1 equals 2. When a population is at equilibrium, the percentage of the population that has a trait isn't changing. That's what it means when something is at equilibrium. So if the distribution of some trait doesn't change over a lot of generations, we say that genetically that population's at equilibrium. It's not changing. So what we want to know about is when populations do change. Like if you had all come back and said, hey, you know what, the evidence says no, humans are not evolving in any way. Then we would say, well, hey, we're at equilibrium. Life is good. We might go out and look at maple trees in Ohio and say, are they evolving? Are maple trees evolving? And if we look at enough maple trees over enough years and determine that whatever characteristic it is that we're tracking isn't changing, then we would say, hey, no, they're not evolving. They're at equilibrium. They are staying the same. And this is sort of a mini unit. We're going to compress it a little bit. But the big question that we want to answer is, when does evolution actually happen? Is it happening all the time? Are all species evolving all the time? That's what we want to know. We have this thing called HardyWeinberg equilibrium. And it's actually a mathematical construct. I'm realizing that color is a little hard to see. We are not going to calculate HardyWeinberg. Okay? It's actually math. And if like Mrs. Halett's academic class does do a HardyWeinberg calculation, we're not. I just want you to understand what it is. There are some HardyWeinberg concepts that have showed up on the biology end of year exam, and I want you to do well to make sure that you get your ticket punched to get out of high school. At equilibrium, the distribution of traits and genes are not changing. They are staying the same over many generations. And what HardyWeinberg says is, that happens when the following conditions are met. When there are no major mutations, we don't get any new traits via mutation. When we don't have any emigration or immigration, we don't have any individuals coming into the population and bringing new genes with them. We don't have anybody leaving the population and taking their genes out with them. It happens when the population is big. Sample size matters. We talked about that early in the year, and we talked about that a little bit with the variation lab. The bigger your sample size, the more likely you are to get a normal distribution. The bigger your sample size is, the more likely that over generations, gene frequency and trait frequency stays similar. Oh, it's frozen again. HardyWeinberg says populations tend to stay at equilibrium when mating is totally random. Totally random. No choice goes into it. This does happen with some species. It happens with a lot of plants with wind-borne pollen. Where plant sperm lands, nobody knows. It goes out into the wind, it lands on another plant, might land on your car, doesn't fertilize anything then. But it's totally random. There's no choice. And populations stay at equilibrium when there's no selection. And we're going to talk about forms of selection. You saw those in your vocab. We had, directional and disruptive and sexual selection. In order for a population to not evolve, there has to be no selection whatsoever. So tomorrow you are going to have a brief video to watch and take some notes on. I will not be here. I'm going to a professional day at YSU for forensic chemistry. I'm excited. And on Monday we're going to pick back up with starting to talk about a little bit more about mutations and immigration, emigration, and we'll have a small activity.